right? Use a proof by contradiction to prove that if X is a rational number and Y is an irrational number, so you're dealing with X being actually a rational number and Y being irrational, and we are saying the sum is actually irrational. So, but we need to use a proof by contradiction. So in a proof by contradiction, we consider the statement P implies Q and um and assume that P is true and Q is false. And we arrive at a contradiction through this. So, right, so we're going to actually assume that P is true. Sorry, to assume P is true, we shall let X be a rational number and Y be an irrational number. Irrational number. So here we agree that the whole beginning is if this is the case, then the implication implies Q when you have P. Okay. Okay. Let X be a rational number and Y be an irrational number. And assume that. Right. So, and assume that. Right. What do we assume? So we proceed to assume that. Right. And assume that X plus Y is a rational number. So we assume the opposite of what is there. Is a rational number. Or you can say X plus Y is not an irrational number. More accurately, we can say that. That is the same thing, right? In this case. Okay, but if it's not an irrational number, then it could mean a couple of other things. But obviously, because we are combining numbers with rationality and irrationality, the understanding is therefore that if the number is not irrational, I mean, we're not limiting numbers here because we have numbers that are neither rational nor irrational anyway. I mean, we have imaginary and complex numbers that exist. So, and assume that X plus Y is not an irrational number. Is not an irrational number. Okay, which will potentially be a rational number then. Right. So I want to arrive at a contradiction. Now, in this case, because you're dealing with arbitrary numbers X and Y, you can suppose that X is equal to the number 2, which is rational. And Y is equal to pi, which is irrational. Okay, because we said Y is irrational. Okay, when a statement is not It's false. You cannot prove a false statement using general arguments because it's false. So you use yes, Saman.
I'm confused at this part.
Yes. Sorry. We can suppose that x, and so in other words, we choose those numbers. So you suppose that x equals to 2, which is rational, and y equals pi, which is irrational by choice, by the axiom of choice. Right? There's a principle in mathematics we call the axiom of choice. So these is true. You can choose these numbers arbitrarily, right, by choice. Why? Well, you can choose anything because since we know this is, well, we experiment with numbers before we prove something. If a statement holds for all numbers, we can always pick or choose, then we can prove it in general. But obviously at this point, we have this. We have this. So what is the conclusion? Hence, x plus y, we chose the numbers, you can choose anything. So hence x plus y is 2 plus pi, which is irrational, which is an irrational number. Which is an irrational number. Therefore, our assumption that if x is a rational number and y is an irrational, all right, y is an irrational number. Our assumption that if x is a rational number and y is an irrational number, then x plus y is not an irrational number leads to a contradiction. Leads to a contradiction.
Hello?
Yes, please.
Can you explain what rational and irrational is?
All right. Good. Yes, so we can explain what rational and irrational is. The rational numbers, rational implies that a number p is rational when if it can be written as in the form a over b, where a and b are relatively prime, p is not zero, a and b are integers. Right, so irrational means we can't write it in the form a over b. So irrational means the form a over b it means P is not equal to these for A and B integers, being integral numbers. But most importantly, be not zero. So this is the essence of irrationality and rationality. But I'll add another uh, hint here. Okay, I said here, hence x plus y is equal to 2 by that is an irrational number. Which contradicts which contradicts which contradicts that x plus y is not irrational. Hey, that is what we get. Because we said that x plus y is not irrational. So we suppose therefore that, so therefore assumption that if x is rational and y is irrational, then x plus y is not an irrational number leads to a contradiction. Thus, if x is a rational number and y is an irrational number, then x plus y is an irrational number. Okay. And this is the case as required. All right. Move on to the next question. Okay, here we're dealing with what we call the P series. And the question is that um, you need to do something. What P series would you use to test for convergence of the series? That one. By the limit comparison test, which is the second comparison test. Now, it's a test I've been using from time to time, the limit comparison test. We're asking the question, what P series is best applicable in this situation? And so really, what P series is the most applicable in this case? Okay, so we can be able to prove that one. Okay. Um, this is how we're gonna do this one. Right. So first, we're gonna say put an divided by 4n squared, 4n to the fifth power, 3n cubed. Okay. Put an to be that. Full stop. The next thing is you need to choose. Make a choice. So you choose Bn to be the highest degrees here. The highest degree, you take the highest degree in the numerator, the highest degree term, and then you take the highest degree term in the denominator. And you can leave out all the numbers there. So I can just choose n to the power 5. Just drop the number 4 in the denominator. You can carry on with it. This is n squared divided by n to the power 5 over 2, and this is the same as 1 over n to the power 1 half. Okay, we've taken down the n squared, so it would be negative there. But this one becomes the p series because it's 1 over n to the p form. Becomes a p series with p equals 1 half, less than 1. So at the end, now this becomes is divergent. Okay, because by a p series, we mean a series of the form 1 over n to the power p from n1 to infinity. There's 3 cases. For divergence, we mean this one. So it will diverge. But, but when p is bigger than 1, then we have convergence. Right, when p equals 1, we have divergence.
Okay.
Yes, please. So what p series would, okay, yes.
Can you explain this part?
Okay, thank you. Right, to explain that part, so when we come to the p series we choose in view of the limit comparison test, we take the highest degree. So here for the Bn, we're going to choose this one, which is the highest degree term, and then we're going to choose this one because those are the terms that have an effect when it comes to the behavior of the numerator and the denominator. But this choice is not unique because another student can even choose the number 4 here, but just that now those numbers cannot change anything here. So we have chosen n squared, and we have chosen the square root of n to the 5th power. Right, and then we simplify like this and we get that. Okay. Right, the next thing now we're going to do, so that is the Bn. So if you answered the question, what p series would you use to test for the convergence of these? So this is the p series, this one here, it's the p series. Use this one here, and this is the p series that they want in the question. And now they're asking, so how to apply this test? It was an interesting way of asking the question, but the examiner is really saying, apply the test. Apply the test. But you see, the way the question is phrased is show how to apply the test. I found that being a language issue, but yeah, doesn't matter. So in view of the test, by the second comparison test. Okay. We have an over bn, and this is the limit. N approaches infinity. What is an? Okay, it is everything that's given. It is the general term of the series. So it is 4 plus n squared, all divided by the square root for n to the 5th power plus 3n cubed minus 7. Right, you divide by Bn, which is 1 over n to the half. So this is the limit. Right, so it becomes 4 plus n squared divided by 4n to the fifth power plus 3n cubed minus 7 over 1. Right, we just divide by the Bn. The Bn is 1 over n to the 1 half. Right, we proceed to the next page. Moving on to the next page takes us to the limit as n approaches infinity of an over Bn. N approaches infinity. Okay, I lost you. My apologies, I had lost you. I had lost you. But yeah, this is recorded, so you're gonna be okay. My apologies, I did not realize that I lost you. All right, so I did not realize I lost you. So this is 4 plus n squared. You divide everything by the square root. 4n to the fifth power plus 3n cubed plus 3n cubed minus 7. Right, so this is therefore multiplied by n to the 1 half. Or this is n to the 5 over 2 plus 4n to 1 half, right, by the square root of this, 4n to the fifth power plus 3n cubed minus 7. So you pull out n to the power 5, or it's going to be n to the what? To the 5 over 2. All right, here you'd have 4 plus, if you pull out n to the power 5 from inside here, this one is going to be 3 over n squared.
Where did this come from?
That one came from the n to the 1 half, n to the 1 half. That's sitting here from the Bn, which was in the denominator. Because the Bn is 1 over n to the 1 half. So if you divide by the Bn, the same as multiplying by the reciprocal, so it's n to the 1 half over 1. Right, so you have 7 over n to the fifth power. All right. Now you pull out n to the 5 over 2 from the numerator, which is 1 here. And here it becomes 4 over n squared. All right. Which is 1 plus 4 over n squared divided by this one here. To the fifth power. So if you take the limits, then it's going to be 1 plus 1 over infinity is going to be 0. And here it's going to be 4 plus 3 over infinity, 0, 7 over infinity, 0. And this is exactly 1 over 2. And this 1 over 2 is different from 0. It's not equal to 0. Right. Um, since the summation, right, since the summation, okay, since the summation here, right, you take the summation here of the Bn from n equals 1 to infinity, which is the summation from n equals 1 to infinity. And the Bn is what? We saw that is 1 over n to the 1/2. Since this one diverges, it follows that this series okay, so here you can just go back to the original things, the original notation. So you can go back and use exactly that notation of the R. You can use the symbol R. Since this one R diverges, it follows that R equals 1, 1, right? Okay, it's from 2, from 2. This summation is from 2. I need to put 2 here. I need to put 2 here. I need to put 2 there. Right, so therefore this one is from 2. Since this one diverges, it follows that this one also diverges. Just copy this one, 4 plus r squared in the numerator. Which is 4r to the 5th power, 3r cubed, minus 7. Since this one diverges, it follows that this one diverges. By the, as said here, this is called the limit comparison test, or you can call it the second comparison test. Okay, that's the one we normally use here in this course. I'm going to comment about the first comparison test. We don't normally use, doesn't involve the limit, it's just comparing the comparison of terms, etc. Yeah, so I'm going to comment on that at some point. But now, so by the limit comparison test, also called the, yeah, diverges by the limit comparison test, or the second comparison test. By the second comparison test. So we have divergence. Why? Why divergence? Divergence is because the P series is divergent because n is 1/2. So we use the small series, which is the P series here. So we can't see that convergence using the whole thing here, this big series. We can't see the convergence in the AN, but we can see the convergence in the small P series. That's why we actually form this P series. But also, this limit here of the AN over BN cannot be 0 for us to conclude. If ever it happens that this limit becomes 0, then we cannot use this the second comparison test or the limit comparison test. Okay, we continue. Right, the next discussion we're going to have is about this one. Right, it's about this one. Okay, let me look at if
Hello?
yes, please.
Can we go over the question I sent in the chat?
Okay, yeah, I'm actually looking at it now. Okay. This one here, proof from first principles use the definition of convergence of a sequence that the sequence converges. Yes, we can do that. So we can prove this one from first principles. Now, to prove this one from first principles, there are a couple of things we need to consider, obviously. Right, a couple of things we need to take into account. What things do we need to take into account? Right, so we're going to look at that now. 1 second. Okay. I'm gonna copy it. And then we're good. Okay, let me put the question here. Let me put it here. It's okay. Previous. Next, previous. Show that screen pointer. Something like that. I think that it might just be. Okay, just 1 sec. Hey, trying to include this question here. Okay, let's look at this question. Right, prove from first principles that is using the definition of convergence of a sequence that this sequence converges. Okay, so it's a very interesting one, but first things first, we need to consider the fact that consider the limit we have this limit of the minus 3n. Right, so we have this. Right, so which is minus 3 over 2n. 2, okay. And then now this limit is 2. This limit is 2. Right, so if you consider that this limit is 2, um, consider that. Thus, we suspect, we use the word suspect, we suspect that the limit. So in other words, it is not a proof what we have done. The fact that the limit is 2, it's some form of suspicion.
Hello?
Yes, please.
How did you get 2?
Okay, that's a good question. When n approaches infinity, here it's going to be 3 over 2 times infinity. Right, so it's going to be 3 over 2 times infinity plus 2, which is 3 over infinity. Right, so infinity is a very large number. So if you divide 3 by infinity, it's going to be 0. So that it's 2. Okay. Now, with these, then, we need to prove now. Prove from first principles. We need to prove from first principles. Right, to prove from first principles, there are a couple of things you need to consider. And we proceed as follows. We need to consider it. Let, okay, so we let epsilon greater than 0 be given. Right, for okay, let me remove the 4. Remove the 4. So let epsilon greater than 0 be given. Thus we have this. Okay, so you have minus 3n plus 4n squared minus 4n squared. So you have minus 3n. Okay, and this is exactly minus 3 n squared here. So but it becomes minus 3 over 2n, which is 3 over 2n, like that. Um, Hence, this is 3 over 2n. It's less than epsilon. This is the same as. Right, you can invert these things and write 2n over 3 is bigger than 1 over epsilon. I've just taken the inverse both sides. So this is the same as 3 over 2 epsilon. Hey, beautiful, beautiful result. Beautiful, beautiful result. We conclude in this block here. Here's our conclusion for this problem. Just going to change the color. By the Archimedean by the Archimedean principle. There exists n in the naturals with now by the Archimedean postulate, if n is bigger than a real number, then you can always get there exists a natural number capital N, n capital N in the natural numbers with capital N strictly larger than the 3 over 2 epsilon. Okay. For such n, for such an n in the naturals, we have we have okay. Um, we have we have n bigger or equal to n, which implies that n is strictly bigger than 3 over 2 pi epsilon. And this implies that a n minus 2 less than, we got that a n minus 2 here was actually equal. So we got that um, a n minus 2 is actually equal to 3 over 2n, which is less than epsilon, since epsilon bigger than 0 was arbitrary. We have we have um, we have the limit of a n equals 2 as n approaches infinity. Okay, so this is sort of the answer to the question. So, but by this, we have proven the result. Okay, right. Next. Okay. Right, let's do this one. A couple of questions I want us to do here about improper integrals of the of two kinds. Okay, there are improper integrals of the first kind. I'm going to be looking at the Riemann integral, but I think that I'll need a little bit more space. So I'm going to move the Riemann integral question to sort of the end there of this so that we have a fair chance to discuss it. Okay, here is one question that says one of the properties of the Riemann integral states that if f is Riemann integrable on the interval AB, then this is that. So this is just a property. A property. This is a law, if you like. So that if Kn is this, then you can take the absolute value of Kn, but the absolute value of the Kn is bounded by pi over 3 and then evaluate that. We start as follows. So we start and take the given. So we given Kn, which is 1 over n, the integral of this one. Nx. I'm just copying the Kn that's given. This question came in the January paper, something. Right, so this is going to be Nx. So these kinds of integrals like these that are problematic, because this one is going to take, okay, I'm going to comment on this. You have to look at the fact that what is the square root of 3 divided by 2? Okay, we shall look at that. And where this integral itself is actually, is it proper, is it improper? Those kind of, we need to investigate this. Right, but first, given this one, we have this here. Yes. So we take this one, which is the square root of 3 over 2. Divided by 1 minus x squared dx. This is less or equal to, right. If you like, you can take the absolute value of the 1 over n, but your the n is positive. So it's less or equal to the integral. Hey, I'm trying to squeeze that there, but I think that we'll have to write at the bottom. Otherwise, I'm going to write on top of the 5 there. Right, but my point is that when we have, what we have here is, this is less than or equal to, we like, you can take the absolute value of this one, 1 over n. And then by this property that these absolute values will just affect only the function and not even the dx. So it's going to affect the nx. Dx. Which is 3 over 2. This is less or equal to, because we also know that if you have the absolute value of the trigonometric functions, like cosine, is less or equal to 1. So we're going to use that here. There is 1. Like this. Okay. Okay, so this is what you get. Right, 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 right. So we get this one. Let's see what we have here. Okay, that's what we have. Right. But we need to show that it is exactly. Mhm. Right, so this is nice. But now you need to remember from first year. Because now you have the integral of the square root. What is the integral of this one from first year? Need to remember this one from first year. The integral of this one is like the integral of this anyway. So it's arcsine of x plus c. So this is 1 over pi arcsine of x. 0, which is the square root of 3 over 2. Oof. Right. So thus, hence, you have this one. Square root of 3 over 2. You substitute the limits of integration, arcsine of 0. And this is that is less than or equal to. What is arcsine of the square root of 3 over 2? Okay, it's like the sign of something is um the sign of a given angle is the square root of 3 over 2. What is that? The sign of 60 degrees. Pi over 3. 1 over n into pi over 3. Okay, and this means we have this one here. This is less or equal to pi out of 3n. Okay. Right, after this, we need to just evaluate the integral, the limit of the kn. So from the previous page, we're able to achieve that kn is less or equal to pi over 3n. Right, which is the limit. Right, you take the limit as n approaches infinity of this one. As n approaches infinity of pi over 3n. Okay. So it is the limit as n approaches infinity of this one, less than 0. Which means that because this is less or equal to 0, the absolute value, and the absolute value is never negative, so it is less or equal to 0. But most importantly, it means you have the absolute value is greater or equal to 0. And then you have the limit approaches 0 here. You have kn here is less or equal to 0. Well, I mean, it's between 0 and 0, so this means that effectively the limit as n approaches this of kn, this limit is 0. Right, is required. Is required. All right, so this is exactly what we had to show, that this limit, we had to evaluate this limit. Okay, we had to evaluate this limit. So this limit is actually equal to 0. Right. We have these. Okay, it's very interesting to look at this question and begin thinking about this. Is this an improper integral or a proper integral? We have to investigate, but it looks proper because it can only be, the problem can only be when x is 1. But you can see it's from 0 to the square root of 3 over 2. What is the square root of 3 over 2? 0.8 something. Okay, smaller than 1. So this limit, within these limits here, this function itself, one of the properties of the Riemann is that if f is a Riemann integrable, then this. Okay, this function itself is continuous and defined. It's defined there, so we do not have any problems. So we can be actually in a position to just easily evaluate this integral here. Okay. Right. One question that is very important, that these are the kinds of improper integrals of the second kind. So this one is an improper because at 3 here, there's 3 here, but if you substitute 3 here in the denominator, it's going to become 0, so you're going to have division by 0. So it's an improper integral of the second kind. Improper integral of the second kind. Okay. All right. We continue. We continue. Right. The question becomes, what do we do with this? And how do we evaluate the integral of a function that is undefined within the domain of integration? First things first, we need to take note of the fact that the function f of x is 1 divided by x minus 3 is defined for, right, this function is defined for x bigger than 3 and continuous on the closed and bounded interval epsilon 4 for for the function. This is defined for x bigger than 3 and continuous on the interval epsilon to 4 for epsilon. However, f is not bounded. However, f is not bounded. Is not bounded on the open interval 3, 4. Is not bounded here. Okay. Right. Okay. Next, we determine the convergence, explain why the following integral is an improper integral, and determine by using limits whether, so we explained why this is what is improper. This is the explanation. and determine by using limits whether the integral converges. So next we determine using limits the convergence of this. Okay. Next, we determine using limits. The convergence or divergence. Right, to this end, thus we have that the integral itself from 3 to 4 of dx divided by x minus 3 is actually equal to the limit as t approaches 0 from the right of the integral of 3 plus t 4 dx x minus 3. The limit which is the ln of x minus 3 3 plus t, then 4. Okay. With that, okay. So now at this point, you substitute the 4 and the 3, and you take the limit. So it's going to be the limit. St approaches 0 from the right. Substitute 4, it becomes the ln of the number 1 minus the ln of, you put 3 there, becomes the ln of t. As this approaches 0, it becomes the ln of 1 minus the limit st approaches 0 from the right of the ln of t. Right, st approaches 0 from the right, the ln of 1 is 0. And this becomes plus infinity. Right, because the ln of 0 is undefined. But the ln of t, as t approaches 0 from the right, is infinity. The integral is divergent. Is divergent. Right, the integral is what? Is divergent. The integral is divergent. Okay. The integral is divergent. All right. So we have done this question. It demonstrates what we do when we evaluate the improper integrals of the second kind. Okay, these are the integrals of functions that are not bounded, on certain intervals. Not bounded on certain what? On certain intervals. But also you look at the fact that the function f of x, which is 1 over x minus 3, is defined for x bigger than 3. It is defined for x bigger than 3, but the function is not defined at 3. But it's because now the x we're dealing with is x between 3 and 4. So the x is x at 3 and the x at 4, and then the x in the middle between 3 and 4. But it's defined for the x's that are bigger than 3, and it continues on the interval that starts from epsilon to 4. We don't put 3 here, but we put epsilon to 4. But for the epsilon bigger than 3, strictly bigger than 3. However, the function f itself is not bounded on these open interval. It's not bounded on the open interval. Next, and that explains why the following integral is improper. Okay, that the function is unbounded. Next, we determine using limits the convergence or divergence, and we've just done that. Okay. Next, we solve more problems. Okay, the next question. Right, there are a couple of investigations you need to do. Like at this point, how do we investigate the following series for absolute or and conditional convergence? Right, we get started. We get started. Right. Okay, we get started. Now this one here uses something very interesting. So we use the integral test. We use the integral test because now we consider the function, and when I have, okay, because this thing can be just integrated. So we put x, we change the r to x for purpose of integration. We leave out the minus 1 to the r, divide by 2x. We use the integral test because this one here implies that. Let's look at this. What is the derivative of this? Okay, you can use the quotient rule to find the derivative of these, but you can use the product rule as well if you convert this thing to a product. And write it is yes. So you have this one here. Which is minus 3 over 2. Okay, let me write properly. So I just find the derivative of this function. What is the derivative of this function? Which is f primed. Right, we can find first the derivative of this one, which is, and then 2. So it's going to be minus, and then it's going to be minus 2 here. Plus minus 1. And then the derivative of that one is minus 3 over 2. One over x. Okay, right at the bottom. minus 3 over 2. You're using the chain rule, so bring down the minus 3 over 2 and then subtract 1, which is minus 5 over 2. And then you multiply by the derivative of the ln, which is 1 over x. And then in view of the product rule, we keep the 2x, the minus 1 constant. See, this is consistent with the product rule. Would have used the quotient rule because it's a quotient, but yeah, it's just that the quotient rule has too many things we need to simplify, etc. Right, product rule, what does the product rule say? It says that y equals f times g implies dy dx is f prime to g plus f times g prime. But in the end, this whole thing is negative. So we use the integral.
How did you get this?
That's a good question. How did I get that? I just moved the denominator, the 2x in the denominator, and I decided to write it as to the power minus 1. So it's just moving it up.
Oh, okay.
Yeah. Okay. And then now I was trying to convert the whole quotient to the product, so I can just apply the product rule of differentiation to find the derivative. Alternatively, let's say one would have used the quotient rule, but the problem with the quotient rule is there's too many things. We need to simplify that. The product rule will just quickly give us the answer. But we can see that here we have a negative, and here we have a negative. So if you take the numbers x, so this is less than 0 for x in the interval from 2 to infinity. From 2 to infinity. Right, from 2 to what? To infinity. Right. So we use the integral test because this one is that sort for that is f, which is ln x to the power minus 3 over 2 over 2x is decreasing. Okay. Then we have that. We get that. Right, so it's decreasing. And then now we just need to integrate that. So we have, therefore, that here at this point, right, so we take this series as it is from 2 to infinity. Ln r, the ln of r, the minus 3 over 2, we divide by 2r. This one yields, it yields the function f of x, which is the ln of x to the power minus 3 over 2 divided by 2x. Hence, we have Jn equals the integral of 2 to infinity, which is minus 3 over 2 divided by 2x dx. Okay, let's call this one here. All right, so this here you'd have to call it n. Okay, I'll call it j sub n, and then we call it like this. Let u be the ln of x. Du is 1 over x dx. So what is the integral of this? There are two variables, x and u. X is from 2 to n. If x is 2, then this one is ln 2. If x is n, then this is the ln of n. This has implications. It means that here, this one is going to be ln 2. This one is going to be the ln of n. We have made ln x u, so this is exactly that. What is the x? So this is 1/2, which is the ln of n, which is u to the minus 3 over 2 du. 1/2. You add 1, it becomes 2 over 2 is minus 1/2. What is the integral of u to the power minus 3 over 2? So if you add 1 to minus 3 over 2, you get minus 1/2. So this is becomes minus 2u to the minus 1/2. The integral of ln 2 from ln 2 to the ln of n. Right, so it's negative here. Minus the ln of 2 minus 1/2. Okay. What is this? 1 over the square root of ln 2. 1 over the square root of the ln of n. Okay. Then you can take the limit. Thus, the limit as n approaches infinity of Jn, which is the limit as n approaches infinity, then 2 minus the square root of this. And therefore, as n approaches infinity, this is going to just be 1 over the ln of 2. So this ln of 2 is finite. The conclusion becomes very clear. The integral test shows that the integral converges. So that's the integral. Converges. And the given series. And the given series is absolutely convergent. Is absolutely convergent. Okay, because the question was saying that obviously investigate the following series for absolute or conditional convergence. So we have seen absolute what? Um, Convergence. So the series is absolutely convergent. Right, next question. Investigate the following series for absolute or conditional convergence. Or it's similar. We continue to do this one. Right. Let's investigate this one for absolute or conditional convergence. First things first. What do we do here at this point? What do we do here at this point? So we proceed like this, as follows. We can let AR, which is -1, I'm gonna use N. Let's just maintain the tradition. Let's keep the tradition. So you let AN be -1 to the power n 1 divided by the square root of n over 2 into 4n minus 3. Okay. Okay. I'll put, I must remove this one. So you take an to be the general term of the given series, but this implies that then we can check the modulus of this. Okay, now you can take the modulus. That's what you get when you take the modulus. That's what you get when you take the modulus. Okay, when you have these, that is our an. And then what can you choose Bn to be here? You can even write it like this. You can multiply it through within the brackets and get a 2n squared minus 3n out of 2. So we have this. Okay. Now, what can you achieve? You can choose anything. Choose Bn.
How did you get that?
Just multiply 3 by n over 2 into the brackets by distribution. So we have 4 divided by 2, which is 2, n by n is n squared. And then we have n over 2 by minus 3, which is minus 3n over 2. Right, so you can choose Bn now if we're thinking of the limit comparison test. Right, so we're going to do that. So in view of the limit comparison test, what do we get? Okay, Bn is going to be 1 over, you can take the square root of this, which is 1 over n. A divergent P series when P is 1, the power there, which is the divergent when P is 1 is called the divergent harmonic series. Divergent harmonic series. Then the limit as n approaches infinity of an over Pn. Right, what is an? It's the square root, it's 1 over the square root. So you'd have 2n squared this. So you divide by that, which means you multiply by that. Minus 3n over 2. N approaches infinity. N divided by, factor out n squared. Take the square root of n squared, it becomes n. You factor out n squared from under the square root, you get 2 minus 3 over 2n. Hey. Limit is n approaches infinity of 1 divided by the square root of 2 minus 2n. If n approaches infinity, this is 1 over the square root of 2, which is not 0. Right, so this is what we get. This is what we obtain. Um, Continue. Right, since the series here, this one, of BR is, we've seen that it became just 1 over, it became just 1 over R. Since this one diverges, this is from 1. Yes, it's from 1 here. R equals 1 to infinity. Right, since this one now diverges, and therefore the series minus 1. R over 2. For R minus 3. Means this one diverges, and therefore that series is not absolutely convergent. Is not absolutely convergent. Okay. Right. 7 marks. Right. Something that you can try and use is integration. So we now apply the alternating series test. Right. We now apply the alternating series test to the summation articles 1 of the AR. Let f of x 1 divided by the square root of x over 2, 4. 4 for x minus 3. Okay, so is 1 divided by 2x squared minus 3x over 2. We need to find the derivative of this because it must be decreasing for us to use the alternating series test. We need the function to be decreasing. So we're going to find the derivative of this one. Okay, let's see the derivative of this one. F primed of this. Okay, first things first, this one can be written as 2x squared minus 3x over 2 to the minus 1/2. The derivative is minus this into 2x squared minus 3x over 2 to the minus 3 over 2. And then you take the derivative of what is inside, which is 4x minus 3 over 2. We use the chain rule of differentiation here. Chain rule of differentiation. Right. Now we have this. Okay, if we have this, then what is next? We can see that this is less than 0, decreasing. Hey, decreasing for the x values which are from 1 to infinity. Now it remains to just show that So thus Fn plus 1 is smaller than Fn for all n which are in the naturals. Okay. And the implication, therefore, is that if you take the modulus of the an plus 1 is going to be less than the modulus of an because this is decreasing and this relation is true for all n which are elements of the naturals. Also, we take, it must be 0, the limit of the an. Right, so it is 0 because if you consider this one here, n over 2 for n minus 3, this is equal to 0. All right, so we have two conditions that are met beautifully. One of the conditions that this limit is 0 and that the function itself is decreasing from 1 to infinity. 1 to infinity is the domain of summation. The conclusion is obvious. Therefore, the original summation with only the minus 1 removed, with only the minus 1 removed, converges, right, converges by the alternating series test. Okay. We continue. We continue. Converges by the alternating series test. And hence, we conclude that this summation we conclude that AR is conditionally convergent. Is conditionally convergent. Okay. Because we're supposed to, at this question, investigate the following series for absolute or conditional convergence, and we've achieved conditional convergence of these series here. Okay. Right, we have a radius of convergence to determine for this one, so let's just practice. Determine the radius of convergence of this series, taking into account that the endpoint of the interval will not be included since the limit of the an. So now you can see the examiner changing the variable r to the variable n for purposes of computing the limits and other things. And so we shall adopt that practice as well. Okay. Determine the radius of convergence of this one. We use the ratio test always. So we let an, which is n squared divided by n squared plus 3. Which implies that an is n squared over that plus 3, which is that. And then we can have the an plus 1 for purposes of the ratio test, which is n plus 1 squared divided by n plus 1 squared plus 3 into x minus 2 to the n plus 1. Right. Remember the ratio test? Hence, by the ratio test, we have right, so you have an plus 1 divided by that, which is the limit. So, which is that one. Plus 3. Which is x minus 2. You divide by that, which is n squared plus 3 divided by n squared, which is x minus 2 to the n. The limit as n approaches infinity. Right, so this is what we have. This is exactly what we get. So this is n plus 1. All squared n squared plus 3 divided by n plus 1 which is n squared. Okay, let's see what we're getting here. I'm just grouping all the n's, the n plus 1 squared, and the n plus 3 here, and the n squared here, and the n plus squared plus 3 here. This one is going to cancel a single n, leaving us with x minus 2. Right, as n, okay, what we get here, we can simplify these, but how do we simplify these? How do we simplify these? How do we simplify this? Okay, proceed as follows. So this is, you can pull out n squared here, you can pull out n here, you can pull out n squared there. So we need to evaluate this limit. So we have n to the infinity. So we pull out n here, it's going to be n squared. And then pull out n squared, so it's going to be n to the 4th power. 1 plus 3 over n squared. So you pull out n here from within the brackets, you pull out there, so that's going to be n to the fourth power. Pulling out an n out of this is going to yield 1 plus 1 over n squared. 3 over n squared. Yes. And then, yeah, since we have this. Right, so upon further simplification of this, so what we have is that we have the limit as n approaches infinity of n to the fourth power. Which is 1 plus 1 over n squared into 1 plus 3 over n squared. N to the fourth power, 1 plus 1 over n, right, so n squared, n to the fourth power cancels out, leaving us the limit as n approaches infinity, 1 plus that, n squared into 1 plus 3 over n squared, divided by 1 plus 1 over n, plus 3 over n squared, into n minus 2, absolute x minus 2 absolute value. As n approaches infinity, it's going to be 1 plus 0, squared 1 plus 0, divided by 1 plus 0, squared plus 0. So this is the same as what? Okay, it's going to be 1 over 1, which is x minus 2. Okay, they're saying determine the radius of convergence of this. Right, so the series most certainly converges for the modulus of x minus 2 less than 1 and diverges. We're interested in the convergence, but just comment on the divergence part. Right, according to the ratio test, when this is bigger than 1, there is divergence. If this is equal to 1, then the ratio test is inconclusive in terms of the divergence or the convergence of the original series. Hence, the radius of convergence is R equals 1 unit. R equals 1 E. Okay. Now I need to check this very carefully. There's a comment I'm going to give just now here. There's a comment, a small comment I'm going to give. Just in a split second. Right. There's a comment I'm gonna give in a split second. Right, so look at that very carefully. Right, right, right. Okay. Right, so let's just obviously look at this. I'm going to conclude this one. Just in a little bit of time, in a little bit of time, in a little bit of time. I'm going to just write the conclusion to this one here. I'm going to conclude this one here. Right. In terms of the radius of convergence of this one. Okay, there's a comment I'm going to give. That is why I'm just pausing, because there's some careful analysis of this that is necessary. Right, so we know the radius of convergence of that. Right, but also we have that this here is less than 1, which means minus 1 is less than this. So now you have that, therefore, if you add 2, 2 minus 1, 2 plus 2, 1, 3. Okay. So note that, therefore, the radius of convergence of this is 1 within this interval. This interval of convergence. Within this interval of what? Of convergence. Okay. Now, this is actually obviously the result. But now I'm looking into what I can add as well to this, because we can attempt to add a small little result. Right. Small little result. But I said already, you can see that the comment here is enough to actually say that take into account that the end point of the interval will not be included. Okay, we would include the endpoints, but they've already told us, so we don't need to investigate that part. We don't need to investigate that part. Okay, so yeah, we're done with this question. But very interesting. That the interval of convergence will be 1 to 3. The endpoints, we don't need to investigate them, but the radius of convergence is exactly 1 unit. Right. Anything else? See, now we have another question. I want to take this question here. This one. Right. So I want to take this question. Right. Let me take this question. Right. So I'm going to take this question and include it in our discussion. I'm going to take it to the end here. For we obtain the following. Right, so the following. Right. Okay. Now I want us to spend some time on this one. Right. So the couple of things we need to note here when we are to focus on this particular question. And um, okay, let's get started with it. Then we shall give lots of the comments as we go along. Let the partition be given, and we need to show that they are in that. But first, it helps to just have an idea of the rough sketch of this function here to make to help us realize that this function. So this one is very similar to the y equals x cubed function, which we learn even at school, the cubic graph. So it's y equals x cubed. But now you can move it 2 units here. So which means that it's just going to be the same graph, but it's going to cut it 2 here. Right, so we have that. So it's going to just be the same graph, but moved up 2 units. So you have y, and then you have x. Right. So this is what you get. All right, this is exactly what we get. But then as a consequence, what we're getting is that it is over this interval from 0 to 1. 0, 1. At 1, it becomes 3. X1 becomes 3. Obviously, we're saying show that the upper and lower sums converge to the same limit. So what is the behavior of the function from 0 to 1? When x moves from 0 to 1, when x increases, y also increases. So this is an increasing function. Hey, you might not need the graph if you can be able to see it's increasing, but the graph makes it easier. You can use the derivative to see that the derivative of this is 3x squared. And then this derivative is bigger than 0 when x is an element of the interval from 0 to 1. So let P be the partition of 0, 1 given by this. Right. We have this. Okay. We continue, but now there are a couple of things you need to remember in terms of this. Would be the way we go about solving these kinds of questions. Right. So if the function is like this, what is the supremum and what is the infimum? Right. That's
How did you get this graph 1 and 3?
1 and 3. Okay, so I picked the x equal to 1 because x lies between 0 and 1. So when x is 1, I substitute into the function. You get f of 1, which is 1 cubed plus 2, which gives us 3. So we have that point. Okay, it's not to scale, but yeah, we have that point there. Okay, this point is very important for us because it actually shows the behavior of the function, but also we're able to see the two values of the function, that when x is 0, the function is going to start at 2. When x is 0, it's going to actually, it's going to run between 2 and 3 on the y-axis. Okay, so we have this. Right. Right, so you continue. So you continue. Right. I will continue. Okay. We have two things that are very important, and they are, okay, the partition is already there, so no worries there. Would have, you'd require the two m's. What is the biggest value of the function? What is the smallest value of the function? This one is the supremum. What is the supremum of the function? Um, okay. And then this one is the infimum of the function. Okay. Now, okay, we have this. Okay, there's something I want to mention here. If you have a function that does this, goes up like this. Now here you have two things. Can you even use it here? Here you have xi minus 1 and there's xi here. So you have xi minus 1 and then xi. Okay, you have xi minus 1 and then what? And then xi. And then if there is xi minus 1, is the xi minus 1 is the one before. So I minus 1 is like the one before. And then xi is what is ahead. Okay, in terms of the ordering of real numbers on the real line. So this is what we have. But then what do we do? Um, okay. At xi minus 1, for example, you would have your f sitting here. It will be f of xi minus 1. The other one is going to be here, fxi. Okay, is what we get. Which one is bigger than the other in terms of the positions on the y-axis? Fxi minus 1 and fxi. You can see that fxi is higher. In other words, the supremum is going to be consisting of fxi, and therefore the smaller one is going to be fxi minus 1. Okay. So what is this now? What is this now? This is I over n from the partition. which is I over n cubed. And therefore, we have this one, which you can see it as f of I minus 1 over n, which is I minus 1 over n cubed plus 2. Okay. Right, so we are in business now. Let's continue. Okay, we'll start with one of them. Maybe we'll start with the supremum. Right hands. Capital M. Capital M. Which is I over n cubed. Right, so this one is I cubed over n cubed plus 2. Now there is lowercase mi. Okay. Okay, continue. Okay, we continue. Okay. Right, so we are good. Okay, you can easily verify the answer to these things. It's not that we can use direct integration straight away, normal rules of integration um to, to deal with this. So here you have I minus 1 cubed plus 2. Right, so we have then the things we need to use, the formulas for the LPN. So LPN, lower, the lower Riemann sum is always, it always takes the infimum, the small one, small m. Okay, let me start with UPN. So this one is going to have a little bit more work because the small m now is having some I minus 1 inside. So if in the exam you can start with the UPN. If the one is, you don't start with the one that is minus is inside, because now then you'd spend a lot of time trying to cube all this. But now I'm going to just, it's a choice. So the choice is you're going to start with this one, UPN. UPN. So you have UPN here. So UPN is going to start with the big M, delta Xi, which is this one. Okay, the delta Xi is just, we can just call it delta X. Right, then just call it delta X, or delta xi. Right, normally it's enough to just call it delta x. Okay, so now we have that. So the delta x is the difference between any two successive points in the partition. So you'd have maybe this one and this one subtract. So 2 over n and that, which is 1 over n. So it is 1 over n. So this is I cubed over n to the fourth power 2 over n. Right, so it is exactly 1 over n to the power 4 I cubed. Plus, and then you can take out the 2 over n, like this. Okay, that's what you get. Let's see, we finish this one off. Right, so what we're getting is that. So UPN is 1 over n to the fourth power. The sum of the I cubed. What is the sum of the I cubed? The sum of the cubes is this one. Sum of the cubes is n squared into n plus 1 all squared over 4. The sum of the cubes is n squared into n plus 1 squared over 4. 2 over n. And then the sum of the 1 is n by 1. Right, if you divide by the n to the power 4, then it's going to cancel out here, giving us n plus 1 squared divided by 4n squared. Okay. That's fine, you can leave it like this. Now continue, we're going to look at the other one. We'll look at the other one, which is LPN. LPN. So it is small mi delta x. What is the small mi? Is this one? This is the number 2. So that's going to be I minus 1 over n cubed plus 2. The delta x is the change is 1 over n. What do we get out of these? Then multiply by the 1 over n here. Summation. Cubed over n to the fourth power plus 2 over n. One over n to the fourth power. Summation. I minus 1 cubed plus 2 over that. 1 here. Okay, now we have this, but we have a little bit of work to do. You have 1 over n to the fourth power. So you cube this one. Cube that is, you have I cubed minus 3I squared. Okay, have this. So this one is 3I squared plus 3 I said squared. So writing a cube there. Okay, you can use the cubing, can cube this using the binomial theorem and other even direct multiplication of this. So here this is 3I minus 1 plus 2 over n into 1 times n. So this is the same as 1 over n to the fourth power into the summation and then this one is plus 3 over n to the fourth power minus the summation plus 2n over n. Okay, right, a bit more work. Need to just evaluate these sums here. I think I'll move to the next page. So made that page available there. So that would be the LPN becomes 1 over n to the fourth power. And the rest of the things. Let's see now. Need to finish this off. Um, we need to finish this off. Right, so we're moving to the next page. I'm just trying to transfer all this last step of the LPN, which is the lower Riemann sum. Right, so what it is exactly 1 over n to the fourth power, the summation, 1 to n cubed here, 3 over n to the fourth power, I1 to n, this one is I squared. So you need to know the sum of the cubes, the sum of the squares, and also you need to know the sum of the natural numbers. I n to the fourth power, um, okay, here, miss something. Right. This is 1 here. For this last one here. So this summation is 1 here. Um, okay, continue. Okay, continue. So, we are we're here, but this is plus twice n over that. Okay, let's look at a couple of things here. 1 over n to the fourth power. The sum of the cubes were given here. Sum of the cubes. N squared into n plus 1 squared over 4. So that one we just write down. The sum of the squares. What is the sum of the squares? We have it. That one. Um, okay, I'll just write it for me now. Don't need to prove it. The notice prove it, but yeah. Um, right. Just write. I'll write it now. Right. The sum of the squares is n into n plus 1 to n plus 1 divided by 6. And then the sum of the one. Okay. Right. Then you have the sum of the um okay, shall we together just now? The summation of the n. Yeah. The summation of the i's is n into n plus 1 over 2. All right. This one is n over n to the fourth power. N plus 1 squared over 4n squared minus. Okay, 3 goes 7 times into 6, it goes 2 times. 2n cubed. So n goes, divides, giving us n cubed. 1 over n cubed. LPN. Okay. The lowest common denominator, I can write 4n cubed. Divide 4n cubed by 4n squared, it becomes only n into n plus 1 squared. Divide this one, it becomes 2. n plus 1 into 2n plus 1. Divide by the 2, it becomes 2. By 3, 6 into n plus 1. Divide this one, it becomes 4. This one is out of 1. Divide this one by that, it becomes plus by 2, it becomes 8 n cubed. So this is what we have. Right, so this one is going to be n squared plus 2n plus n, which is n cubed plus 2n squared plus n minus. This one is n by 2n, which is 2n squared by 2, which is minus 4n squared. This is exactly n plus 2n, which is 3n minus 6n plus 1, which is minus 2 plus 6n plus 6 minus 4 plus 8 n cubed. We divide everything by 4n cubed. Okay, let's see what we're getting here. It's a bit lengthy. A bit lengthy, so we have this. Um, anything, any like terms here? Um, okay. And then now you have the cubes. Let's deal with the cubes. This one and this one. It's 9 n cubed. The squares. This one and this one, minus 2n squared. The squares, the linear. You have these ones canceling out, and then we're left with only n plus n. Okay. And then now you have 6 minus 4 is 2. 6 minus 4 is 2 minus that 0. Divided by 4n cubed. All right. Let's see what we're getting here. So this thing here, this n, which is a common factor, and put the numerator and denominator, giving us 9n squared minus 2n plus 1. You divide everything by 4n squared. All right. See what this is giving us. Now with you now, I'm just checking the arithmetic, if the arithmetic is correct. Just 1 second. Right, I'm checking the arithmetic if it's correct. We're going to conclude our discussion now, but yeah, I need to make sure that we get the correct sums, because there can always be some small errors in these things here. Right, the summation. Okay, I'll be with you. I'm also doing verifications of this here. Right, so you have x cubed. If x cubed plus 2, that is the original function. Right. So this is correct, this. But what about this one? Um, let's see now. Okay, just checking. Just checking properly everything here. Okay, cube. And then now this one. Okay, I'm just checking the working. Did I put the 2 there? Yes, I did put the 2 there. So if you put the 2 there, so it's the same. It looks very correct. Because this one here, if you look at these, okay, this must be very similar to each other. So if it's like this, then the other one must look like this, or yeah, it can always look like this. Because if you look at this here, they must look very much the same. They must just differ by a sign. But at the moment, so you square this one, which is exactly n squared plus 2n plus 1, and then you add that one, it's going to be 8n squared. You divide everything by the 4n squared, which is 9n squared plus 2n plus 1. Divide everything by 4n squared. Okay. Nine n squared plus 2n plus 1 over 4n squared. So yes, these things are correct. Okay, this one is just that it's plus 2n in the middle, and this one is minus 2n. So yeah, they're both correct. Show that the upper and lower sums converge to the same limit. Hence, the LPN, we've seen the LPN is what? Is this one? Is 9n squared minus 2n plus 1. 9n squared minus 2n plus 1 divided by 4n squared. Okay, we're here. We're back again. Right, so divide by 4n squared. Divide by 4n squared, but also we have that the UPN. Right, we're finishing, please. I know we've dragged much. We've been sitting on the screens for some good amount of time now, so we need to conclude our discussion and take some short break. So this is going to be 9n squared plus twice n plus 1 divided by 4n squared. Okay, you can see that the UPN is 9 with the plus. It's a plus 9n squared plus 2n plus 1 over 4n squared, and the LPN has just minus 2n. Right, so we can be able to take which is the limit Sn which is 9n squared minus 2n plus 1. So which is the limit which is 9 over 4 minus 2n over 4n squared plus 1 over 4n squared. We can just write this. Okay, to evaluate the limits. Here you have UP. The limit is n approaches infinity of the LPN. UP, UPN. Yeah. Um, this one is U. Right. So this is the limit. 9/4 plus 2/4 squared plus 1/4 squared. As n approaches infinity, is 9/4. As n approaches infinity, is 9/4, which means that the LP is 9/4 and the UP is 9/4. So obviously this means the upper and lower Riemann sums converge to the same limit. So show that the upper and lower Riemann sums converge to the same limit. Okay, so we have that. We have that. We have that the upper and lower Riemann sums converge to the same limit. Okay, the conclusion we can draw here, right? The conclusion we can draw here is that they converge to the same limit. Okay, so we then say hence LP is UP equals 9/4 so that the upper and lower Riemann sums, the upper and lower Riemann sums the upper and lower Riemann sums. Okay. The upper and lower Riemann sums. So the upper and lower Riemann the upper and lower Riemann sums. The upper and lower Riemann sums converge to the same limit. Well, thus, this means therefore the integral from 0 to 1 of the function f of x dx, this integral from 0 to 1 of the function x cubed plus 2 dx. Okay, what is this integral here? This integral, it's x to the 4th power over 4 using first year techniques. Okay, just that we are doing things here using partitions. Substitute everything here. 1 to the 4th power over 4 plus 2 into 1 minus 0. 4 by 2 is 8 plus 1, 9. So this integral is 9/4, which is equal to LP, which is equal to UP. Okay, so we confirm that this integral is 9/4 using all available methods, or at least most of the available standard methods of integration. Okay, and we are done. And now the time is approximately 1943. We started at about 17 hours. So we did pretty well, time-wise. Yeah, my aim was to actually just add a little bit of 20 minutes beyond the 2 hours. Yeah, but we have a lot to do tomorrow. Right, I must thank you for joining us. I will see you again tomorrow. Same time, 4:30 in the afternoon. Hey, goodbye.